As you know, every term MTL selects a doctoral thesis that has been defended in the last few months for the MTL Distinguished Doctoral Seminar Award. And with the outstanding research that takes place in MTL, as you can imagine, this is a very competitive process to select our awardee every term. And so I'm particularly delighted today to bring to you Alex Guo, who is the MTL Distinguished Doctoral Seminar Awardee for the fall of 2016. So Alex is a native of China. She obtained her bachelor's degree in electrical engineering and computer science from UC Berkeley, and a master's degree in ECS from MIT under my supervision. She did a master's thesis on molybdenum ohmic contacts to indium gallium arsenide field effect transistors. And then for her PhD, she's also been doing research under my supervision on the instability of gallium nitride MOSFETs, a very important problem, as Alex will present, that somehow is today the bottleneck for the deployment of a very important technology that is going to transform electrical power management. Alex obtained the U.S. National Defense Science and Engineering Graduate Fellowship for 3 years. And she also obtained the Best Student Paper Award at the 2016 International Reliability Physics Symposium, which is the most distinguished conference in the field of electronics reliability. She also was a research intern with Intel in the summer of 2013. I think in addition to the tremendous technical accomplishments of Alex, she has a true vocation for service that she has really exercised at MIT and in MTL for the benefit of all of us. She's been a tremendous citizen of the community and has played many leadership roles at MIT. She was a graduate community fellow in the Office of the Dean for Graduate Education. She was vice president of the MIT Graduate Student Council. She was the leadership development chair of the Graduate Women and also in MIT Executive Board. She was the chair of the MIT Grand Gala 2012, the social chair of MARC 2016, and many more that it will take a long time to list here. And for her service to MIT, she received the MIT Graduate Woman of Excellence Award in 2015. And so as you can see, we're bringing forward here a very distinguished scholar and member of our community, and it gives me a great pleasure to give the MTL Distinguished Seminar Award to Alex Guo today. So, Alex.
Oh, man.
Don't drop it on your,
Thank you.
On your foot.
Wow, it is heavy.
It is heavy. So, your honor. Thank you.
Good afternoon, and thank you, Jesus, for the wonderful introduction. It's a great pleasure to be here to talk about my PhD work. So for the past 4 years, I have studied the bias temperature instability, or BTI, of gallium nitride MOSFETs. And this work is supervised by Professor Jesus Del Alamo, and my two committee members are Professor Dimitri Antoniadis and Professor Tomas Palacios. So this work is done in MTL, obviously, and it is sponsored by MIT MTL GaN Energy Initiative and also the United States National Defense Science and Engineering Graduate Fellowship. Oops. So here's a brief, quick outline of today's talk. I'll start by talking about the background of this work, and then I'll explain the experimental methodology. And following that, I'll present the results we have and also discuss both the recoverable degradation of BTI as well as the permanent phenomenon of the BTI degradation. And I'll summarize this talk with key contributions. So start from background. First of all, why are we interested in gallium nitride for power electronics? First of all, you may or may not know that gallium nitride is a wide bandgap material with the bandgap of 3.4 electron volts. This gives rise to high breakdown voltage or breakdown field. And this makes gallium nitride very attractive for energy efficient power management in a wide range of applications, from, for example, the lower voltage consumer electronics such as the laptop charger, or all the way to electric vehicle, solar panel, and wind turbine. and gallium nitride has a lot of potential. And the graph here on the left really summarizes some of the advantage of gallium nitride in comparison with the more traditional silicon devices, also the more recent silicon carbide pretty well. As I have mentioned, the electric field is pretty high for gallium nitride. It's much higher compared with silicon and also higher than silicon carbide. The energy band gap of gallium nitride is also higher than silicon, and it is on par with silicon carbide. It also has pretty high electron velocity compared with silicon, and it's a little bit larger than silicon carbide. Because of these advantages, gallium nitride is really attractive for high voltage operation applications as well as high frequency switching devices. So growing gallium nitride is expensive compared with silicon. So in order for it to, to manufacture gallium nitride, we need to be able to make it cheaper. And recently, we are able to grow gallium nitride on silicon, which is a very key advancement to make gallium nitride really push it to the market. So what you see on the right is a gallium nitride MOSFETs, which I will explain what it means later, on the 200 millimeter silicon wafer. So with this, gallium nitride is really ready to become commercialized. So how does a gallium nitride transistor look like? What you see here is the cross-section of a gallium nitride HEMT, stands for high electron mobility transistor. So on top of the material property I told you earlier with the high breakdown voltage, because we have all-GaN layer grown on top of the gallium nitride, it produces a large polarization effect that spontaneously produces high-density 2D electron gas with very high mobility. Because of this, the gallium nitride HEMT is the basic structure for high-frequency gallium nitride transistors. For high-voltage application, the most favorable structure is the gallium nitride MIS-HEMT. MIS-HEMT stands for metal insulator semiconductor high electron mobility transistors. So what it is that on this gallium nitride HEMT structure, we insert a oxide layer. With this inserted oxide layer, we can achieve lower gate leakage current and in turn, a larger gate swing. So on the other hand, because we add this oxide layer, it also gives us more stability and reliability challenges that are more severe or present in the HEMT structure that we're familiar with. One of these really serious reliability issue is the bias temperature instability, or BTI. BTI is the threshold voltage or VT instability when you apply a gate bias stress, especially at high temperature. And BTI can cause electric parameter degradation and eventually cause circuit failure. So on the left side, you see is a typical experiment people do to test what is the BTI. So we apply a VGS stress, so a stress on the gate, and it can be positive stress, which will produce PBTI, or negative, we call it NBTI. And on the right-hand side, what you see is an example of a negative VT shift as a result of NBTI when we apply a negative 70 volt stress on the gate for 500 seconds at 125 degrees C. So from this IV characteristic, you see that before the stress, the device is mostly off at 0 volt, but after the gate stress, the threshold voltage has shifted about -1 volts to the negative direction, and now at 0 volt, device is no longer off if we're talking about power circuits. So that's very unsafe, and it's very bad for circuit performance. So as you can see, that BTI is very important for us to address in order to have reliable performance of circuits. So BTI has been observed in gallium nitride MIS-HEMT. Both PBTI and NBTI has been reported. And on your left side, you see a recent work, a paper that published in IDM, where the authors observed a large positive VT shift when they apply a 7 volts gate stress at room temperature. On the right-hand side is a work reporting the negative bias temperature instability, where the authors observe a large negative VT shift when they apply -10 volts at 90 degrees C. So the magnitude of delta VT shift is quite large for MIS-HEMT, And in comparison with silicon devices, it's much larger. So it's a major concern that we need to address for gallium nitride mishap. But it's very challenging because the physical mechanism behind the BTI is not very well understood. So before I talk more about the mishap BTI, it's helpful to look back and see what people have done for BTI in more established material systems, such as silicon. So the very first observation of BTI was actually made in 1996 by a group of engineers in Bell Labs when they study the silicon MOS capacitor. They see a negative VT shift after a negative gate bias stress, and it's not recoverable. So that's the first observation, and about 10 years later, the very famous reaction diffusion model was developed to explain this phenomenon, and it contributes this NBTI to defect generation between at the interface of silicon and silicon oxide. And they think that because of the release of hydrogen from the passivated silicon hydrogen bond, it caused the permanent defect generation at the interface. Even though the observation of a BTI was made very early on, there's established model for that. BTI was really not a big issue until 2000s when nitrogen is introduced to the standard CMOS process. This is because nitride oxide has more water species and gave rise to NBTI and make it more severe compared with the previous generation of transistors. Also around the same time, the high K dielectric was introduced to continue the transistor scaling trend. And because the high K oxide are known for having a lot of oxide traps, it gave rise to PBTI. So around 2000s, the BTI study has attracted a lot of attention, and a lot of people start to study different kind of models, trying to understand the physics. So more recently, the silicon carbide devices has their also observation of BTI, where the authors contribute that mainly to the oxide trapping and detrapping phenomenon. So there are a lot of new model has been evolved, and the most prominent is probably the two-stage model that I'm showing here. Basically built up on the previous RD model. What we have here today is the first is the oxide trapping detrapping mechanism, and at a kind of a benign or lower gate stress. And then when we elevate the stress, you will see a defect generation, which is the second stage. Most recently, with the development of 3.5 material, BTI has also been observed in InGaAs and has been studied in the other 3.5 material systems. So let's come back and look at the BTI in gallium nitride mishap. And I talked earlier that we don't quite understand the physics behind it. And what is the reason for that? Well, it's mainly because, as you can see, the cross-section here, there are multiple layers and interfaces, and that make the picture quite complex. On the right-hand side is a recent work studying the threshold voltage instability in mishap. And then authors in this work suggest there are trapping sites inside the oxide at the interface as well as in the barrier layer. And it's very difficult to separate the effect of each of them to BTI. So because of that, in our work, we use a simpler gallium nitride MOSFET structure. So these are industrial prototype devices with featuring a recessed gate. So what you see is, what you see is that underneath the gate, the GaN cap and the all-GaN layer are etched away. So this gives us the opportunity to isolate the oxide and the oxide gallium nitride interface and study their contribution to BTI. Today, my talk will focus on the composite dielectric. So it's the silicon oxide on aluminum oxide as the gate dielectric with the aluminum oxide adjacent to the gallium nitride channel. The EOT is around 40 nanometer. We have also studied the silicon oxide devices, and if you're interested, I'll be happy to provide papers or we can have a discussion offline. So to summarize, what our goal in this work is really to understand the physics behind BTI and to mitigate BTI in gallium nitride MOSFETs, and hopefully can understand better what's happening in gallium nitride mishent. Okay, next I'll talk about our experimental methodology. So first, experimental setup. This is our lab, the setup for all the experimental work I've done on the 3rd floor. And what we use is a Keysight B1500A device, semiconductor device analyzer connected to a Cascade probe station. And we use the RF probe tip, GSC 125 micrometer. And this chuck is connected to a temperature controller. You can now see from the picture there is behind the station, but it helps us to do all the temperature measurements. So all the work measurements are done in air and in a dark chamber, and the ground, the substrate is grounded. Our group have developed a characterization suite in C++ to automate most of our experimental work. So here is the experimental flow. We start from device screening and initialization. So in this step, we also extract very important device figures of merits, and they serve as a reference for the rest of the stress and recovery experiments. And then we apply a constant DC bias stress on the gate. And during this period of time, we pause the stress periodically and perform a very benign IV short sweep to extract device figure of merits, basically trace how they change during the stress period. After the removal of stress, we continue to monitor the change of device figures of merits for a period of time to look at how they recover. Now, sometimes it take a very, very long time for device to recover, depending on device time constant. So what we end up doing is to develop a thermal detrapping process to speed up the process. We basically bake the device for a period of time, and then that will speed up the process. And at the end of the thermal detrapping, we do another complete IV sweep so that we know if the device is completely recovered or if there's any permanent degradation that took place. Now I will explain our figures of merits definition. What you see here is IV characteristic that are done at VDS at 100 millivolts. And first, we'll define threshold voltage. So our VT is defined as the VGS value, which is the gate voltage, at which the drain current reach 1 microamp per millimeter. And then we define the subthreshold swing, which is the inverse slope of an IV characteristic on the semi-log scale. And we define that at ID equals to 0.1 microamp per millimeter. The maximum transconductance, GM max, is also extracted from the same IV characteristic. So these are the three major parameters that we study in this work. The first sample comes 1 to 2 seconds after we remove the stress. That's basically how long it takes for this characterization to finish. Okay, so now I will go into our results and briefly discuss what we have found. So here's the overview of the BTI behavior of the gallium nitride MOSFET that we have studied. On the left side is the typical behavior of PBTI, and there are two regimes of behavior here. So what you see is that when we apply a positive gate bias stress, the first we see a positive VT shift. You see the delta VT is positive. So delta is basically the change of threshold voltage, and the increase with stress time. And then this is the first regime. And the second regime is what happens after we thermal detrap the device, where we have a residual permanent positive VT shift that is not recovered. Next, we look at the NBTI side of the picture, and there are three regimes here. Here we stress the device at negative 10 volts at 175 degrees C, and we see that regime 3, which is a small negative VT shift at low stress time, and it becomes positive, and this is regime 4, where you see this positive VT shift. And then as we continue to increase stress time, we see a leftover or a permanent negative delta VT after thermal detrapping. So next, I will study or report the 5 different regimes separately. And I will start from the recoverable degradation due to BTI. And in the picture I've shown you earlier, there are 3 regimes that belongs to the recoverable. So it's regime 1, regime 3, and regime 4. And I will start from 1 and 3 because they have the same mechanism. Okay, so in regime 1 and 3 is both PBTI and MBTI at relatively lower stress voltage. What we first look at is at room temperature, the stress time dependence of delta VT. And we use 10 different stress voltages at room temperature and see how delta VT change over time during stress and also during recovery. What you will first observe is that under positive bias stress, you see a positive VT shift, and for negative bias stress, you see a negative VT shift. And they have this very symmetrical behavior, and as we increase the stress time, the magnitude of delta VT increase. And delta VT also increase as the magnitude increase of the stress voltage. After recovery, and especially after final thermal detrapping, we see that the delta VT shift are completely recovered for all 10 stress voltages. Next, let's look at maximum transconductance, delta GM max. And we again see a symmetrical behavior. But the difference in this picture compared with the earlier one is that for MBTI, we actually see a temporary boost of GM max. And for PBTI, there's a degradation of GM max. And after recovery and final thermal detrapping, the GM change are completely recovered. So the last parameter we study is the subthreshold swing. And in this stress voltage regime, there are very minimal subthreshold swing change. So as you saw earlier, that the main change in this stress regime is the delta VT and delta GM max. So we plot the correlation of the delta VT and delta GM max for both stress and recovery for all the 10 stress voltages. And we observe they are linearly correlated throughout stress and recovery, which indicate that for both PBTI and MBTI, they probably have the same one single mechanism that are responsible for the VT shift. So our observation at the room temperature is very similar to what people have seen in other material system, which is contribute to oxide trapping. So we use a very well-known oxide trapping model on our experiment data with the model shown on the left side here. So in this equation, A is a prefactor, gamma describes the stress voltage dependence, and N here describe the stress time dependence. So we use this model on our experimental data, and on the left side, we show the T stress time dependence. And our experimental data yield an N value of 0.16 for PBTI and 0.44 for MBTI. So these N values are very similar to what people have reported for in-gas system as well as the gallium nitride MISHAM devices. On the right-hand side, we studied the VGS stress dependence, and we got a gamma value of 0.33 for PBTI and 0.9 for MBTI. So this gamma value is also similar to what has been reported for gallium nitride MISHAM from other groups. So we talked about mostly the stress regime, and now let's look at the recovery, which give us more insight on what's happening behind the BTI. So what we do here is to normalize all the recovery data to the first data points and look at the recovery. And we see that they overlay on top of each other very well despite the difference of stress voltage for both PBTI and MBTI, and they kind of have the same slope, the recovery rate. We also look at the temperature dependence. In this set of experiments, we fix the stress voltage. So for PBTI, we stress the device at 2 volts, and for NBTI at -2 volts. And we repeat the same experiment at different temperature from -40 degrees C to +40 degrees C. And again, we trace the stress time evolution of delta VT. And what you see here, you can probably see that for PBTI, there seems to be less of a temperature dependence compared with NBTI. And that is indeed the case if you look at the Arrhenius plots on the right-hand side. The activation energy of NBTI is about 0.37 electron volts, and it's only 0.087 electron volts for PBTI. And so next, we also look at the recovery for temperature dependence. Again, we normalize all the data to the first data points, and you probably can observe that PBTI recovery has more of a temperature dependence compared with NBTI. And indeed, the activation energy of PBTI is 0.15, which is higher than NBTI recovery, which is 0.056. So our study so far encouraged us to postulate the trapping mechanism for the first and third regime, which we believe is the oxide trapping and detrapping from one single band of defect within the aluminum oxide that are very, very close to the gallium nitride channel. So we believe that this defect band extends from below the Fermi level of the channel and to extend above to beyond the conduction band of gallium nitride channel. And the distribution of this band is probably following a Gaussian distribution. So the dynamic of this oxide trapping is shown here with the energy band diagram. So initially, when devices are at rest, there are trapped states under the Fermi level inside the oxide. When we apply a positive gate bias stress, there are more states become available because they become below the Fermi level, and the gallium nitride channel can supply electron to be tunneling into these sites. That will introduce a positive threshold voltage shift. After the removal of the positive stress, the electron can again be released back into the gallium nitride channel. And as you can see, there's a little bit of an energy barrier. That's why we saw earlier that there's a temperature dependence. And let's look at the NBTI. And this picture is actually very similar to PBTI recovery, where the electron that been trapped inside the aluminum oxide can escape into the gallium nitride channel. And there can also be an energy barrier, and that's the reason that earlier you saw there's a temperature dependence for NBTI stress. And when we remove the negative bias from the gate, again, the states become available underneath the Fermi level in the aluminum oxide. Therefore, the electron can directly tunnel into these states. So there's a symmetry. So PBTI stress and NBTI recovery are very similar, and PBTI recovery and NBTI stress are very similar, when the PBTI stress and NBTI recovery show less of a temperature dependence. Okay, so I have talked about regime 1 to 3, and now I will talk about regime 4, which is also on the negative bias side, but it's recoverable. What's very interesting about regime 4 is that you see this positive VT shift, which is really a unique phenomenon of gallium nitride system that hasn't been observed in silicon or silicon carbide. So that's very interesting for us to study. So what we do first is, again, look at the room temperature, and we change the stress voltage from -10 to -20 volts, and we again trace the stress time evolution of the 3 parameters, delta VT, delta S, and delta GM max. And you see that even though at the beginning there's a slight negative VT shift, which we have just discussed, after some stress time, they turn around and become positive. And this positive VT shift increase with the stress time, and stress also increase with stress voltage. And accompanying that, we also see a change or increase of the subthreshold swing and a slight decrease of maximum transconductance. And at the end of the thermal of the experiment, after thermal detrapping, all the device degradation are completely recovered. Here is the correlation of delta VT versus delta S throughout stress and recovery. And you see that they're very well correlated. Again, it suggests that the change of delta VT and change of delta S is probably from the same single mechanism. So what we believe that is happening is a phonon-assisted tunneling process where the electron in the valence band can tunnel through the deep levels within the gallium nitride channel. And this could happen at the edges of the gate, underneath the gate, when we supply a negative gate bias stress. With this assisted tunneling, it will lift off the band, energy band at this region, and they show up as an effective increase of doping level. And as a result, you will see a positive VT shift. After we remove the stress, because the energy barrier here for the electron are low, thermal detrapping is effective for the electron to get released. Therefore, this is a recoverable process. So to summarize what we have talked so far about the recovery degradation of the BTI, first, at the low stress regime, we see that there's a very symmetrical behavior of VT shift for PBTI and MBTI. And we believe that this is due to oxide trapping and detrapping in the one single defect band within the aluminum oxide. And our data match very well with the oxide trapping model that people have been studied in other material systems, as well as gallium nitride mishemmed. And we also look at the very peculiar MBTI behavior at mid-stress, where we see a positive VT shift, and that is due to the trapping in the gallium nitride substrate at the edges of the gate. Next, I'll move on to the permanent degradation part due to BTI. And so we have covered regime 1, 3, and 4, and now I will talk about 2 and 5. And I'll start from PBTI. What you see here is at the room temperature, we stretch the device at 5, 10, and 15 volts, and we want to focus on these leftover or permanent degradation at the end, where you see that there are a pretty large leftover positive VT shift after 15 volt of stress. And this is accompanied by a degradation of GM, but not so much the subthreshold swing degradation. So to study this permanent phenomenon and also distinguish that from the total VT shift that we measure, what we do is that on a typical experiment, we capture the total VT shift and GM degradation, and then we bake the device with thermal detrapping, and we extract the permanent portion. And then the difference between the two values will be the recoverable part that I have reported to you earlier. So through this process, we're able to only look at the permanent degradation. And here is the correlation of this delta VT and delta GM, which is the two parameters that have permanent degradation for PBTI in high stress. And we see that they have a very good correlation, linearly correlated. And this suggests that the change of these two are from one single mechanism. And we believe that is due to the generation of near interface oxide traps in the aluminum oxide. The similar observation has been made in silicon high K metal gate devices, as well as in gas system with high K dielectrics. So for MBTI, we first again look at the room temperature data, where we stress the device from -10 to -70 volts. So what you see here is really very similar to the mid-stress regime I talked about earlier, the regime 4, where you see a positive VT shift. But for each one of them, we have also extracted the permanent portion, which we collect after thermal detrapping, and you see that there's a permanent portion of delta VT that also increase with stress time and the stress voltage. We have done the same with the two other parameter, which is delta S and delta GM. Both parameter has permanent degradation, and they all increase with the stress time and the stress voltage. So here is the correlation of all three parameters in one graph, and in here I also add all the temperature data that I didn't get a chance to show you. But as you can see, ranging from negative 45 degrees C to 125 degrees C and negative 50 volt to negative 70 volts, all the data we have here are have a very nice correlation, linear correlation, which again suggests a single degradation mechanism for this MBTI at high stress regime. And what we believe was happening is the interface state generation under high negative gate bias stress, where the defect can be generated at the aluminum oxide gallium nitride interface, and after the removal of stress, they are left behind and not recoverable. So this is a very well-studied mechanism in the silicon MOSFET systems, and there's a lot of reference on the web that you will be able to find. So to summarize the permanent degradation part for PBTI under harsh stress, so what we study here, the 15 volts stress at room temperature, there's a permanent positive VT shift that is not recovered. And this is due to the generation of near interface oxide traps inside aluminum oxide. For NBTI, there's a negative non-recoverable delta VT, which is accompanied by the change of subthreshold swing and degradation of maximum transconductance, and we believe that is due to the interface state generation. So with that, I will summarize our key contribution of this work. So what we done was first we developed a measurement scheme to characterize BTI in gallium nitride MOSFETs. So there's a benign characterization scheme that we calibrated that do not contribute further the device degradation, which offer fast, reproducible, and accurate measurements. We have also calibrated a benign initialization and reset step, which is the thermal detrapping step, to help us speed up the recovery process, also distinguish the recoverable phenomenon from the permanent degradation. Next, we provide understanding of BTI in gallium nitride MOSFETs. So the VT instability we have studied are due to three different kind of phenomenon. First is for the benign gate stress, there's this trapping, detrapping symmetry in oxide, as I have explained earlier, that this defect bend inside the aluminum oxide. And for NBTI, we have this additional positive gate bias, positive VT shift, which is due to the gallium nitride channel trapping under the edges, at the edges of the gate. And lastly, when we increase the stress voltage to pretty high voltage, harsh stress, there are additional interface state and near interface oxide trap generation. So this work provides the fundamental understanding to elucidate the reliability and the instability of gallium nitride for high voltage application for gallium nitride mishap. With that, I'll conclude my talk, and I welcome any questions.
Thank you, Alex. We can take questions now. Sure. There's a microphone here, Charlie. Do you mind?
Well, then they're going to record what I asked.
Yes. For posterity.
Alex, that's a terrific talk. Thanks.
Thank you.
I guess a long time ago, I worked on these the silicon dioxide interface, and we had this nitride and oxide kind of combination that Simon Wong at Stanford developed. And one of the things I think you said earlier that I was a bit confused on is that at the early parts of silicon, when it degrades, basically either a threshold shift or as you're talking about subthreshold shift, slope change. The model that you talked about was that when there was a bias stress, the hydrogen could be kind of removed and then expose the trap. And that made sense to us. And what we then found was that what happened was the nitrogen that came from an ammonia piece actually filled that trap, removed the hydrogen, filled that trap, and kept it more stable. So that's a long story. Now to my question. What I was wondering, is there anything in what you're doing here? It seems like the traps are all formed, and all of the things that you're talking about are the electrons coming in and out based on where they are in the bands and so on. But is there any sort of change of the traps, either increase or decrease with this bias temperature stress?
Okay. So basically, are you talking about the creation of new defects?
Either the creation or the annihilation. You know,
Okay.
getting rid of them or making more.
Okay. So are we getting rid of them or are we creating more? It's really depending on the reference spot at the beginning. So one of the challenges to find what is the initial state, because when we get the device, it could have already been some traps there. So we can only say relative to that beginning state, we're maybe generating more defects, or we're not generating except instead we're doing trapping, detrapping. So I guess in our case, for both PBTI and NBTI, when the stress is high enough, we do generate defects at the interface, also at the aluminum oxide, in the oxide. The exact location of these traps and why they are formed is not, we don't quite understand the physics behind that yet.
Okay, I think I see. So you've never seen that the traps kind of decrease we only create them.
Okay, so I guess for the recoverable part, we do see a little bit. For example, when we have the NBTI, so we apply negative bias stress, we see that device maximum transconductance actually increase. That's because you can say temporary annealing of some of the traps in the oxide. But that is a temporary effect, it's not permanent.
Okay. And one last question. Did you do any CV characteristics of these devices? Just make VDS equal 0?
Yes, we did a CV characteristic. I didn't have time to have them, but I have the data and I'll be happy to share with you.
Okay, thanks so much. Great
You're
talk.
welcome. Thank you.
More questions? Yes, do you mind to go to the microphone?
Hi, I have a question about how is there any research on the way of your depositing of the aluminum oxide or the way of your passivating the gallium nitride surface that can change your defect state or the generation of this kind of surface defect?
Sure. I guess what I can tell you is that people have done different type of oxide. So, and what they have found is that if you deposit aluminum oxide versus silicon oxide, for example, you have 1 order of magnitude less interface state, basic defects at the interface. That's why people use aluminum oxide. As far as to improve further, there are different ways that people, my industrial partner have been using different cleaning technique, whatever, to make the interface better. But I'm not exposed to that specific technology, what they're doing.
Okay, thank you.
I'm not sure if I answered your question.
Yeah.
Yeah, okay.
More questions? Yes, please. Go to the microphone, please.
Hi.
I was wondering if you had a chance to control the samples with a GaN on. I'm assuming all of these samples were GaN on silicon.
Yes.
So they have a lot of dislocations.
A lot of what?
A lot of dislocations.
Dislocation, you mean where? Yeah, there's dislocations, yes.
Yeah, so I just wonder, like, if you had any chance to control it with like a different material which didn't have any dislocations, just like GaN grown on like single crystal defect-free GaN, because maybe that can because like we don't really know like what are the causes of these interface defect levels. So like how do you know that it's the oxide and it's not the dislocations in like GaN on silicon?
Well, so depending on which regime we're talking about, there are defects in GaN for sure. But personally, I don't have control over the growth part of
Okay,
this
so all of this
sample.
was only on for like GaN on silicon.
Yes, they are all GaN on silicon. And And yeah, so every generation of device I get, there are some improvement. But what they did exactly, I don't know.
Thank you.
Yeah.
Questions?
Yeah.
One more quick question. Does your testing environment that would change somehow your result? For example, maybe you can have you tried testing under maybe nitrogen ambience or oxygen or air or vacuum? Does that change your testing result?
Yeah, that's a good point. So for at the very early stage of the work, when we first calibrate the different testing environment, I have compared having the nitrogen versus in air, and it didn't seem to give much difference as far as the testing results. However, with some of the low temperature measurement, I do have nitrogen flow in the chamber so that I don't have any condensation.
I see. So basically, they're all trapped in the interface, not something that is related to that.
I believe it's not related to
I
the
see.
environment.
Okay. Thank you.
Thank you.
Any more questions? Yes, please.
First of all, congratulations, Alex. Very nice
Thank
talk.
you.
And I have a question quite broadly. So, considering the electron trapping in existing traps and the traps creation in your dielectrics, do you think there's a real future for GaN MOSFET for power switching applications?
The answer is, of course, yes.
Okay.
I think that right now we're still at the stage trying to understand these instabilities. And if we do understand where they come from, then we can figure out how to fix them. For example, if interface is the problem, then maybe there are different cleaning technique when you do the deposition that can improve the interface quality. And if it's the oxide, well, high K oxide not intrinsically, but it does have a lot of trapping problem. But I think a lot of people are working towards that. So understanding the physics of the BTI or other instability will help us to improve our the fabrication technology. So I think that will, again, MOSFET have a very bright future.
Yeah. So you believe that there's a perfect insulator for MOSFET GaN?
I don't think there's such thing as perfect, but I think for whatever, it depends on the application you want to apply it to, as long as past the threshold that can be reliable enough for a certain application. I think that's what we're shooting for.
What do you think is the tolerable VT shift, the margin?
That also depends on the application. So there are some model that people have, let's say for silicon, they say, okay, what is the 50 millivolts shift lifetime? And they have a benchmark that way. For gallium nitride, we don't really have that because we haven't established what would it be tolerable or not at this point. But I mean, we can certainly, at some point, maybe in the near future, we'll be able to establish something similar to silicon.
Okay.
Yeah.
Thank you very much.
Thank you.
Any more questions? Well, if not, thank you, Alex, for a great talk, and congratulations again on a very well-deserved talk.
Thank you. Thank you.